Huh. Of course. Simplistically, a vector is a starting point, let's call it P, and a direction. Let's call the end of it Q. Now it looks like a ray. Rays start and then they go off to infinity in one direction. Vectors are a little bit different. This has a finite length. And the length of it is the length of the line segment, PQ. The arrow is only there to show you which direction you're moving in. And the way I think about these is, if you start at point P and you're traveling to point Q and you're bearing, remember bearings? The fun things, this is like north some degrees east. The bearing would be the direction you're traveling in, and the length of the vector itself is how fast you're going. So it would be saying, well, I'm going at 45 miles per hour towards Q in that direction. So basically, a vector is has two components, a magnitude and a direction. And lots of things can be described with vectors. Wind speeds, like this picture here is a hurricane, and it shows you vectors of the wind speeds, and as the vectors get longer, that means the wind speeds are stronger. Plus it shows you what direction they're in, and hurricanes, you know, they curl in on themselves. So their wind is almost like a tornado going around and around. Other things that are applied to vectors as forces, like me standing on this floor is applying a force to the floor, and the floor is pushing back and holding me still. So vectors have a lot of applications in physics, mostly physics, but other aspects. All right, so when we talk about a vector, generally we're going to denote it. I try to write my vectors kind of fancy, vector V. You put a little line on top of it like an arrow. Other vectors we're going to deal with, vector W and vector U, are generally the three letters that we use, U, V, and W. All right. So when we talk about vectors, let's say we have this vector, let's call it V, and we have this vector, let's call it W. And when you're drawing your notes, it doesn't have to matter direction and magnitude. Pretty much what I want to show you now is what can we do with these vectors. Now vectors, it's located here, this W1, but technically you can pick up this W and put it anywhere on the board or anywhere in this room, as long as it points in that direction and it has a specific magnitude, a specific length. So there's a few things we can do with vectors. Number one, we can add them. And one way of adding them is to set them off at the same point. So basically what you're going to do is you're going to pick up W and you're going to drop their endpoints, their beginning points at the same place. Now this is just one of the methods, there's another point. So if I pick up W and I drop it right here, and I try to keep the same direction and magnitude, you can plop it down right there, as long as they're parallel to each other. All right, to add them, this is the way I think about it. You have a rock here, and you have these two people pulling on ropes in these two directions. And the blue one is being pulled a little bit harder than the red one. So which way would the object move if they kept pulling in those same positions? Would it go closer to the blue or closer to the red? It would go closer to the blue because the blue is pulling a lot harder. So one way to depict this is to draw a parallelogram. So that red dotted line would be the length and the direction of the blue line up above. And this dotted line, hopefully, would be the length, erase a little bit there. It's supposed to be a parallelogram. And then the sum of those two angles would go smack dab right down the middle. So here would be the vector V plus W. That's one way of doing it. Yes, I'll ask you to draw vectors and add them pictorially and subtract them pictorially. So be prepared to draw. Lots of fun. Rulers come in handy. All right, what if I wanted to do v minus w? So this one here is v plus w. What if I wanted to do v minus w?
Two opposite directions.
Which one do I have to put in opposite directions?
W.
The w. Negative means you're going to pull it in the opposite, complete opposite direction. So when I line them up, let me try to draw a v again. If I have v here, going in that direction, oops, that's an ugly arrow. And then w normally goes here. This would be just regular w.
You want to swing it to the left.
Then negative w would be over here. So if you're going to add them, you would add v plus a negative w. So you'd have v plus a negative w. So your parallelogram that you would form is here and here. And that would be v plus a negative w. And your vector would be going in this direction. So far so good? Not too bad, right? Vectors are always fun. It's geometry. Neither of these is the best case scenario. They require a lot of drawing of parallelograms. So there's got to be a shortcut for both of them. So let me come up with a shortcut for v plus w. So here is v. And if you notice from the parallelogram, this side is w, but so is this side over here. And it's facing the right direction if you draw your arrow. So if you just put it start point to arrow, the diagonal or the finish of the triangle would be their sums. So if you just started with putting w in this position, their sum would be this line. And this would be v plus w. And it makes it a lot easier because you're really only drawing the two vectors and then your solution. So for addition, that's actually kind of easy. Subtraction, well, that's a little bit different. The answer to the subtraction is here. So one way of doing it would be putting your negative w here and then drawing your vector. There is one more way, and I'm trying to think of what it is. Right now it's not coming to me. Sad. Well, let's do it that way though. So you plot your v, you plot your negative w, which would be here, and then your solution would be, let me do it in a different color, this vector. And this would be v minus w. And here is v. Still not coming to me. There's another way of doing it. I just don't remember it.
Are you saying that way's not right?
No, it works perfectly fine. I'm just trying to think of a different way of doing it. Oh. Well, that's not it either. Well, that'll work for now. If I come up with the other one later, I'll show it to you. Of course, all of this is just drawing. It has nothing to do with, well, a specific magnitude or a specific direction. This is just the basics of what you can do with the vectors. So far you only can do two things. Add them, subtract them, change their direction. We can also change their magnitude. So if you start off with a vector that's this long, how would you make it this long? You could add another piece to it, but maybe it's 3 times as long. So you would just multiply it by 3. So when you do something like that, you start off with a vector v, and you want something 3 times as big, I'll put that in quotation, then what we're going to do is what's called a scalar multiplication. So that would be 3 times v. This is called a scalar product. So it just takes your vector and makes it 3 times as long. If it was -3, it would make it 3 times as long in, well, the opposite direction. So you would be talking about, if it's 3 times as long, this would be 3v. And it'd be 3 times as long. Same start point, same direction, just longer. More magnitude. Now, there's a reason I'm calling this one a scalar product, because later we're going to be talking about something called a dot product, and that has nothing to do with scalars whatsoever. Scalars is just a real number. This is a real number, this is a vector, and they have nothing to do with one another other than it makes it 3 times as long. And I think that's where a lot of people get confused. Vectors are not numbers. Vectors are this other thing that we're going to be talking about. 3 is just a regular old number, so we just call it a scalar, because it scales it to be bigger or smaller. All right, so let's start talking about specific vectors. That subtraction one's going to bug me. Actually, I think I have it. V, regular W, and this. If you go from the end of W to the beginning of V, this is V minus W. That's the one I was thinking about. So you set up your V and W starting at the same point, and if you start at W and end at V, that becomes V minus W. Now the confusing thing here is you're starting at W at the end of W, but W is in the second position. So if I gave 2 vectors that look like this is V and this is W, how would you draw W minus V? Where would you start? If V minus W over here starts at the end of W and finishes at the end of V, then how do I do W minus V?
Start at V.
Start at V, end at W. So there's a couple problems in the book that do that, so you just have to be careful. Some tricky ones too. All right, how about we change this into coordinate system? So, little coordinate system. Let's put a point out here. Let's call it the point A comma B. It's a physical point in a coordinate system, so A units to the right and B units up. We can designate a vector just using another point. So let's put another point over here. And let's call it CD. Now, depending on which way you want your arrow to go between these 2 points, you can travel from AB to CD, or you can travel from CD to AB. So if we call this point P and call this point Q, and we start at P and end at Q, then we say that this vector is equal to start at P, end at Q, arrow. This is the vector PQ, it's also the vector V if I wanted to. If I move it the other direction, start at Q and end at P, then the letters have to flip around too. The first letter has to be where you're starting, the second letter has to be where you're ending, where the arrow is. Does PQ have to go right there in the first quadrant?
No.
No, because vectors you can pick up and move anywhere you want. Where would you want to move it? Where would be the most logical place to put it? Logical.
On the
Place.
origin,
Which point would you put on the origin?
the AB.
The AB point. So you're going to take P and move that whole point over here to the origin. Let's do it first and then talk about how. So let's make this P prime. P prime. How did you move P there?
Moved it down.
Moved it down B units
Moved it.
and moved
Left A
it
units.
left A units, right? So if I'm going to keep this vector same direction, same size, and everything else, whatever I did to P, I have to do the exact same thing to Q, transformation, right? Translation, actually. So I have to move it down B units, and I have to move it left A units. So down B, left A, and then I get this point over here, we'll call it Q prime, and we get this vector. So what's true about the vector PQ and the vector P prime Q prime? What's true about those two vectors?
They're the same.
They're exactly the same. So PQ is the same as P prime Q prime, which is basically the same as vector V. That's why I like the vector V notation better than the P and the Q one. All right. So what coordinate is this point at? If you went down B units and left A units, what coordinate did I land Q prime on? If I took Q, which is coordinate CD, and I move it down B units and left A units, what is my coordinate now?
Negative A, negative B.
Nope. I would say it would be negative A, negative B if Q started at the origin, but it didn't start at the origin.
It'll be negative A, positive B.
No. It has coordinate CD. How do you move it down and left?
C minus A.
C minus A. I'll give you that one. So this would be C minus A, comma,
D minus B.
D minus B. That would be its coordinate. Right? You know, you take away from the y coordinate and you take away from the x coordinate.
I drew this graph like really small. It's like the size of my thumb.
It's too small.
You putting this much up there.
Too small, too small. So another way of denoting this vector, and the book doesn't cover this, this is good notation to know, it's shorthand notation, is you can call this vector C minus A, comma, D minus B. Now the assumption of calling your vector this, vector V, with these weird, I don't know what you would call these. Carrots? Carrots go up though. So there's a brace of some kind. Bracket of some kind. I forget the name of them. It looks like a less than greater than, but it's not. You could denote vector V in this notation. This becomes your end point. The beginning point is assumed to be the origin. Alright? So if I gave you a vector W, and I said the vector W is 2, negative 3. With those fancy little brackets, things on the end, greater than, less than. All you have to do is plot 2, negative 3, and your vector W would be this vector. And there you go, it's done. So it's a very quick notation of what a vector is. And there's good reasons to use it, and then there's other reasons that you really don't want to. You don't want to. So far so good? Not hard. So when you see that notation, beginning point is always the origin, the end point is always the coordinate. It's always that coordinate, 2, negative 3 in this case. So the next thing up is, we'll deal with them individually, magnitude. Later than usual.
I know.
Now remember what a magnitude is. It is the force, the length, the size of the vector. Short vectors have small magnitude, long vectors have big magnitude. So a magnitude of a vector, we're going to denote this way. Some books denote it this way, and tell me why I don't like this way.
Absolutely.
It looks like absolute value. But the understanding is, if you have a vector on the inside, this is actually magnitude. So if you see it with just one line, just realize the thing on the inside is not a number, so you can't take the absolute value of it. But you can find its magnitude. I like the double bar, that's how I was taught. But I think modern notation is starting to learn this way. And that's that, modern notation, I'm not that old. So, how do I find the length of W? The magnitude of W, what could you do? Pythagorean theorem. You set it up as a nice little right triangle. You know this side is 2, you know this side is 3, well, technically negative 3, but I'll put it in there, it doesn't matter. And then you go, well, the distance of W is the square root of 2 squared plus negative 3 squared, which is 4 plus 9, square root of 13, right? So we could say that the magnitude of W is equal to the square root of 13.
What's the buzzer saying?
What's what?
What is that buzzer saying? Oh, Shamaka.
Yeah, that thing over there senses it, and it knows where I am on the board.
Okay.
It's kind of cool if you think about it. You hear it very well. I don't hear it very well. I'm old. So, formula for magnitude. The magnitude of a vector v is equal to the square root of 2. Went right here, right? Negative 3 went to the second spot. So we're going to call it a squared plus b squared, where v is equal to a comma b. So you just take the components. These are called components. 2 and the negative 3, they're called components. You take the sum of the square of the components and square root it, and then you find your magnitude. So it's a nice, easy formula. Why would you want something that is a unit? What do we use units for?
To measure.
To measure things. If we didn't have units, we wouldn't be able to scale them. If you have an inch and if you have 12 inches, that becomes a foot, and that turns into another unit. So coming up with something called a unit vector, they're scalable real easy. If you want something 3 times as long, you multiply 3 times 1, and all of a sudden it's 3 units long, instead of worrying about partial units. So where this one is the square root of 13, if I want to make it 3 times as long, it's kind of messy, it's 3 times the square root of 13. But if W was a unit vector, then its magnitude would just be 3, which is kind of nice, rather than 3 times the square root of 13. So how do you think we come up with a unit vector for W? If the length of W is the square root of 13, how do I make it 1? Seriously, how do you take the square root of 13 and make it 1?
Divided by the square root.
Divided by the square root of 13. So the formula for the unit vector is you take a vector and you divide by its magnitude. This guarantees that the magnitude of the vector is 1, because you're dividing by its magnitude. Another way of writing this, if you don't like mixing scalars and vectors, this is a scalar, 1 over the magnitude of v times a vector v. So if vector v has a magnitude of square root of 13, divided by the square root of 13 makes it be 1. It's a nice little easy formula. Now I try to denote unit vectors with u, but sometimes that gets messy because later I might have to use 3 vectors. So another way of denoting it is this. V with a little hat is equal to v divided by the magnitude of v. The hat means unit vector. So if you see a little hat on top of a vector, it's guaranteed to have a magnitude of 1. Guaranteed. V hat.
Where you said little hat is 1.
The magnitude of this vector would be 1.
The magnitude
The length of it.
of
You'll have to catch up later.
Okay.
I know you're going to be like, what? But that's because, well, not mine.
Not mine either.
I know. It's not hard. You'll catch on. So, for example, if I have a vector w and it's equal to 7 minus 4, what is w hat equal to? W hat. I love that hat. Dunn's hat, I guess. Birthday hat? Celebratory hat. So you need to find the magnitude of w. So you do that off to the side. It becomes the square root of 7 squared plus negative 4 squared, which is the square root of 65. Does that break down? 65? 5 times 65. 13 now. That's not going to break down. So the w hat is going to be 1 over the square root of 65 times 7 negative 4. Now you can write it that way. That's one way of writing it. Or we'll get to the other way later because I can't prove it the way this notation is.
So you just leave it there?
Right now, yeah. Actually, that's the best way to leave it. I'm going to show you a different way, but I have to prove that it actually works. I can't just go, hey, and we can do this. And it's a miracle. Now, I said that notation is really good for vectors, except for one problem. You can't prove addition of vectors with it, you can't prove subtraction of vectors with it, and you can't prove scalar multiplication with it. So I got to change notations just for proof purposes, but it's actually a messier notation. You'll see. So what I'm going to do, coordinate system again. And on this coordinate system, I'm going to create 2 vectors, both starting at the origin, one going in this direction, and one going in this direction. And the magnitudes of both of those vectors is 1 unit. So it's reaching this coordinate here of 1, and it's reaching this coordinate here of 1. So these are guaranteed unit vectors. Their magnitude is 1. We're going to call the one going to the right I, with a little hat on top of it. It's not I, the complex number I. It is a unit vector called I. The book denotes them without the hat. They do bold. They'll do a bold I and a bold J. You just can't see bold when I write up here on the board. This other one over here is going to be J hat, or bold J, when they type it. But for your purposes, you're not going to be able to draw out a darker I or a darker J, and that becomes a pain, so just get used to the hat notation. So this is I hat, that's J hat, the unit vectors. So the magnitude of I hat, guaranteed, is 1. So if I want a vector longer in that direction, that's very, very easy. The magnitude of J hat, of course, is going to be 1. As long as I put a hat on top of it, the magnitude has to be 1. So here's the cool thing. If I want this coordinate over here, and let's say it's at 3, 2. My vector is at 3, 2. And here's my vector. Let's call that V, just for fun. I can scale the I side and the J side to create a parallelogram that surrounds the vector V. What's special about the parallelogram I can draw? If I just go straight up and straight left, right, what kind of parallelogram am I going to get?
Square.
Close, no cigar. The sides won't be equal. If I go straight up and straight right, what kind of giving my answers away. What?
Rectangle.
That's going to be a rectangle, right? So all I have to do is scale my sides on the I and the J side, so maybe another J here, and that would bring me directly across from that point. And another I and another I on that side, and that'll bring me directly down. And it creates a parallelogram and this is the diagonal of it, so that's the sum of those two things, right? Well, how far is, what is the length of the side, or how do I denote that side?
2j.
2j. So this would be 2j hat, and this side would be
3i.
3i hat. So another way of denoting vector v, besides 3 comma 2, is now to call it, well, let me put it down below, get my little arrows in there, 3i plus 2j. And this is what the book does all the time. They do the ij notation, where I prefer the point-looking notation. I think it's easier to work that way. But once we start proving things with the ij's, we can go back to the old notation and just start using the patterns. So let's prove a few things. Wish we could go back to classes the other way, where you're just sitting here doing work. Or do you like lessons better? Me personally, I'd rather just give you work. But... What about v plus w? And let's let v equal ab. Let's w be cd. Where a, b, c, d are any real numbers that we want them to be. Alright. To show how this works, you can't use the components. You have to use ij notation. So what we're going to do is we're going to rewrite AB in terms of ij. So this becomes AI plus bj hat as vector v. And then w becomes ci plus dj. Now this is all just regular old math notation, and you can treat I and j as variables. So what would be your next instinct? Combine like terms. So when I combine the ci and the ai, what does that combine to be? Are we multiplying them? I thought we were adding them. A plus c with parentheses around it and the I on the outside, right?
Yeah.
Because you would factor out the I, and you would get A plus C I plus
B plus D parentheses
J hat, and you would get that. So if I go back to my original notation, A plus B plus CD, I'm sorry, AB's component plus CD's component would be A plus C and B plus D. So if I have the old notation, now I can see how to add them. So here's AB plus CD, and the answer is going to be A plus C, the first component plus the first component, comma, B plus D, the second component plus the second component. So it allows us now to use the better notation than rather I's and J's all over the place. So I prefer you do it this way, but this is the proof of why it works. That's the proof of why it works.
So we just proved that.
We just proved with I's and J's that you can combine two vectors together and then rewrite it as components if you wish.
So that's all we was just doing?
Just proving it.
Okay.
Before we had to draw, you weren't here, but we were drawing vector v and vector w and coming up with their sum pictorially. You don't have to do that anymore because this will do it for you.
Okay.
For example, if v is equal to, let's say 1, 7, and w is equal to 3, negative 5, what is v plus w? So what's v plus w? It'd be 4
and 2.
and 2. Add the first components, add the second components. Done. Pictorially, this is
So we
even
can
better.
do that in our head. We don't have to go back and show all that.
No. That's why when you make a proof, you use the information from the proof. You don't prove it over and over and over again. Don't you remember geometry?
Yes.
So sad. You used to prove a little thing and then use that little thing to prove other things. And once you had a proof down, it became a theorem or a corollary.
No, what I'm saying is I don't have to write that proof ever.
Well, I might ask you to.
Okay, that's-
the right name.
I might actually say prove that the sum of two vectors is this.
Alright, yeah, that's what
Yeah, I might ask that. All right, so let's do this pictorially and see what it looks like. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm trying to make the spaces even space, but it never works out for me. All right, so where's V? Oh, V is 1, 7, so 1, 7. So V is this vector. There, so that's B. W is 3, -5, so he's over here. 3, -5, and that's W. So where's V plus W? Well, it's 4, 2. So you go 4, 2. And it would be this vector. V plus W. Now, does that look right?
No,
Why?
it just don't look right.
The sum of vectors is the diagonal of a parallelogram.
Oh.
And it is this diagonal of a parallelogram. So it works out perfectly fine. Drawing it is a pain in the butt, but if you could just do the math and plot it on a piece of graph paper, it actually works out much better.
So how would we do that without that
Without what?
proof?
Oh, well.
Oh,
then
you don't actually.
You'd have to draw the parallel. You would draw V and W. You would draw the parallel side of W down here. You would draw a V down over here. And then you would take W and draw its parallel side over here. And then the diagonal becomes their sum. Tricky. This is much easier. All right. What about difference? What if I subtract them? What's the only thing that changes?
If what?
If I subtracted my vectors, V minus W, what's the only thing that changes?
The
Well,
sign.
that becomes a minus, and this becomes A minus C, and this one becomes B minus D. So you get A minus C and B minus D. So that's not too bad. What about scalar? I'll do a quick proof of scalar. Put it right here. So if I have a vector V, that's AB, and I want to find, how do I denote a scalar? Let's make it N. N times V. Okay, so this is actually N times A comma B. So you can't prove anything this way. So you have to change it into IJ notation. So this becomes N times parentheses AI plus BJ. Now N is just any real number. Actually, any number you want it to be. Even complex, it really doesn't matter. But what can I do with the N now that I have this expression, which is not in my weird vector notation? Distribute. So this becomes ANI plus BNJ. So if I went back into its component form, this would just be AN and BN. So it distributes over the components. The scalar distributes over the components. So it's kind of cool. I'll let you do that. All right, so that leaves pure notation. This is my own title. This has nothing to do with the book. Pure notation of vector. What is a vector? From the very beginning. A magnitude and a direction. But when you write a vector componently, or IJ notation, you get no sense of magnitude or direction, specifically. So what pure notation is you talk about its magnitude, and just by looking at it, you can tell what its magnitude is. And you talk about its direction. And just by looking at it, you can tell what direction it's going in. So where the component and the IJ notation kind of fail in the magnitude direction part, though it gives good pictures really quickly and you can calculate very fast, it really doesn't talk about individually how big is it and which direction is it going in. So I need to do a little conversion. Let's throw a vector up here. Nice first quadrant one, V. And let's say it ends at the point AB. So basically, V is equal to the components AB. We already know how to find the magnitude of it. So how do you find the magnitude of it? A squared plus B squared all square rooted. So the magnitude of V on this side is the square root of A squared plus B squared. So we already know what the magnitude is. That's great. How would you find the direction? No, but direction. I mean, how would you define direction? If you're going to travel a certain direction and you want to be really precise with it, what do you need to have in your hand?
Compass.
A compass. And a compass is designed how? It has north, south, east, but how do you know which direction you're pointing in, other than the arrow moving? And what does it cross over to measure? Degrees. Angles. So direction is always based on angular measurement. So the angle of interest here is right here. So how do I find that angle theta?
Find the lengths of the sides.
Find the lengths of the other two sides. So create a little right triangle. How long is this side?
A.
A. How long is this side? B. How do you find theta?
Tangent.
Tangent. So you would say tan of theta is equal to B over A. By the way, B over A, that looks kind of familiar too. What's another description for B over A? B over A. B, which is up and down, A, which is left, slope. So when you do tangent of theta is equal to B over A is slope, so therefore so is tangent of theta. Which is kind of cool if you think about it, that there's this relationship between a trig function and slope. Alright, so we have this set up, and we can find theta pretty simply by going theta is equal to tan inverse of B over A. With one slight little problem. What quadrants does tan inverse work in?
First and
First and
third.
fourth. First and fourth. So if your vector is in the second or third quadrant, you're going to have to do a little extra of adding pi or subtracting pi, that kind of thing to get to your right answer. So if this one was in the third quadrant, it would be tan inverse of B over A, but then you'd have to add pi to your answer to get the right angle, because you're pointing in the other direction. So there's a little, you have to be careful with that inverse function still. You also still have to know what quadrant your vector is in.
So wait.
We have to use tangent.
Yeah. Because all you're going to be given is B and A. Now you can find the hypotenuse. I mean, that's no big deal. You know, magnitude.
I mean, I thought we did.
That's an uglier number though. B and A are just so nice. That's 2, 3. You know, something nice. But you could. You could use different functions, but this is the one that they normally go for. All right. While I'm thinking about it, is there something else I can replace, well, that coordinate with? I mean, this is the magnitude and this is the direction, but I want a notation that takes the entire vector, still as a vector, shoves it into a notation where you can see the vector's magnitude and see the vector's direction, and it's still the vector itself, rather than having, two separate pieces of information. Well, let's do a little fun stuff. If you look at this angle theta, and we're looking at b and its magnitude, what function does that associate with? Sine. So let me write that down. Sine of my direction is equal to b over, and I'm going to write a magnitude of v rather than the square root of a squared plus b squared. That just takes too long to write. I can do the same thing for cosine. So cosine of theta is equal to
A over magnitude.
a over the magnitude of the vector, the hypotenuse side. And I can solve for a and I can solve for b. And you get a is equal to the magnitude of v sine of theta.
That's B.
B, sorry. And then over here, I was going alphabetical. A is equal to the magnitude of v cosine of theta. So what's nice is a and b as a coordinate is also the components a and b. So I can say my vector v is now equal to the magnitude of v cosine of theta, comma, the magnitude of v, from over here, sine of theta. And just looking at it, you know what the magnitude of the vector is, and you know what direction it's going in. And it's still the vector AB. Kind of cool if you think about it. Now there's one little simplification I can make on this. They both have this magnitude of v, which is a scalar, and both of them have it, so guess what you can do to it? Or do I have to change it to IJ notation?
Just take it out.
Just take it out. I can factor it out. So another way of writing it is vector v is equal to the magnitude of v, cosine of theta, sine of theta. And this is what's called, I would say, pure notation, or magnitude direction notation. Why the heck would we want to do that? Many, 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 many reasons. Where theta is equal to the tan inverse of b over a, and the magnitude of v, of course, is the square root of a squared plus b squared. Why would I want to do that? So let's say I have, as a vector, a force pulling on this point in this direction with 150 pounds of force. What the heck does that mean? 150 pounds of force. Have you ever gone fishing?
Yeah.
Have you ever weighed your fish?
Yeah.
No? How do you weigh a fish?
I have
Little thing you hold on to.
yeah, and it's a spiral.
It's got a little hook,
And it,
pulls it down. A spring. There's a spring on it. How do you weigh yourself when you get on a scale, right? How do scales work?
the same.
There's a spring inside, and as the spring compresses, it measures your weight depending on how far the spring compresses. So you can measure 150 pounds of force by using a spring on a rope, and then just constantly pulling with that force. Let's say also that this force is going in the direction of, let's make it weird, north, 35 degrees east. Where does that angle 35 degrees go? Does the angle go here?
No.
Or does the angle go here?
Yeah.
Yeah. So this would be 35 degrees because you're 35 degrees because you're moving in this direction 35 degrees off of north. the east direction. All right, that's not helping me with my notation. What angle I need is this one down here. So what's the measure of this angle?
90 minus 35.
55? So this is the direction, according to vector language, that we're going in. We're 55 degrees off of the x-axis. All right, and then what I want to do is come up with a name for this vector. Let's call it v. So how would I write v? I don't know its components, but I can find them. To find them, all I have to do is find the magnitude of v. What's the magnitude of this vector?
150.
150. Because it's the force, it's the size of that vector. So you put 150 out front, and then you times it by the vector's direction, which is?
55.
Don't write 55 though.
Cosine of 55.
Cosine of 55
And sine of 55.
and sine of 55. And that would be its magnitude and direction. Now that's not standard notation for a vector, so you have one more step. Take a guess what it is. Distribute the 150, calculate cosine of 55 and sine of 55. I have no idea what they're equal to. But thank God for calculators. So the first component is 150 times cosine of 55. 86.0. I mean, that's kind of boring. So vector v, 86, comma, and then 150 times
122.
sine of 55. 122.9. And there you have a standard vector. That's cool, huh? No? What was it that time? For you. Now there's a few other things in the book.
We're not doing it.
Oh, I'm going to do one of them. The rest of them are, you get to play with. I'm not going to worry
But
about
this
this
one's
one.
likely to be up.
I'll send you the homework in the email.
Alright. You're gonna upload this to YouTube this weekend?
Should be up by tomorrow.
Alright.
I'll start processing a little bit of it today. It takes like a half hour to crunch it all down. One last thing. On page, I think that's all. 19. That's fine, you can figure that out. Okay, on page 746. Oh, I did forget one type of vector. I just saw it. It's called the zero vector. And it's denoted this way. Be really careful. This is a vector. The vector component is 0, comma 0. Or 0i hat plus 0j hat. If I was going to plot it, it would be a point at the origin. And that's it. That's all it would be. Do not confuse this with 0. This is a 0 vector because it has that little line on the top, the little arrow. This is the scalar 0. So if you went 0 times a vector, guess what you get out of it?
0.
Nope.
The vector.
What vector?
0 vector.
The 0 vector. Because what happens is you get 0 times, let's say, AB. You would distribute it, you'd get 0 times A and 0 times B from the IJ notation distribution. And then 0 times anything is
0.
0, so you'd get 0, comma 0, which is better known as the 0 vector. So 0 is a scalar and 0 is a vector are two different things. So don't get them confused. So that's the 0 vector. The other part of it is the properties of vectors. They have the addition properties and the scalar multiplication properties. Lots of fun. Which one do you want to prove? What looks easy? Number 2,
Oh, okay.
associative property. So if you have 3 vectors, vector v, vector w, vector u. Are my 3 vectors. These properties, if you kind of recognize them and you can use them, they shorten some of your work sometimes, so knowing some of them might save you some headache. But I just want to talk about proving it. So when you do associative, it's always adding, well, only with vectors in this case, you can only add 3 vectors at a time. But the sum thing only works as a binomial operator. That means you can only do it on 2 things at a time. So you either do it to the first 2, or you do it to the last 2. First 2 or last 2. And the answer has to come out exactly the same. So that's what you want to prove. So you pick a side, you manipulate it, kind of like an identity, to force it to look like the other side. So it's like a trigonomic identity. So you start off writing things in components. So this would be AB plus CD plus finally MN. It's probably easier with I's and J's. Ooh, that's going to get messy. Let's just do it this way. It's possible this way too. All right, so when you add these 2 together, what do you get?
A plus C, B plus D.
And then off to the right is this MN. So far, so good. All right. Now I can take these 2 and add them because it's 2 vectors and binomial operations work perfectly fine. So this becomes A plus C plus M, comma, B plus D plus N. Bracket. Now what you want to do is take this answer and force it back into this form. So because you can bring vectors together with addition, you can also rip them back apart as 2 separate vectors. How do you want to rip them apart? Well, when we added the A plus C plus M, we got this A plus CM. But we want the C and the M together so we can get U and W together. So what I can do is kind of separate away a vector here and write it as A comma B plus C plus M, D plus N. Is that legal? I mean, if I added those together, do I come back to the vector I started with?
Mm-hmm.
Yeah, it's just decomposing it rather than shoving it all together. All right, well, what is this over here? Well, this was originally the vector CD plus the vector MN. And therefore, you have just moved the parentheses over to the second 2 numbers, second 2 vectors. And there's your proof. Ta-da!